I told you you could always count on me, darling. From that day on, I made a vow I'll be there when.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So before we get into the nitty-gritty of MO energy diagrams, I wanted to tell you guys about bond order. So bond order is the number of chemical bonds between a pair of atoms, and basically it indicates the stability of a bond. For example, in diatomic nitrogen, which is like this, you would know how to draw this based on Lewis structures. The bond order is 3 because it has 3 bonds. On the other hand, in the case of acetylene, which has a triple bond in the middle again, the bond order is also 3, and the CH bond right here has a bond order of 1. So bond order and bond length indicate the type and strength of the covalent bonds between atoms, so this is really important. And so I wanted to show you guys how to use the MO energy diagrams in order to figure out the bond order really easily. So the equation is bond order is the number of electrons in the bonding molecular orbitals minus the number of electrons in the anti-bonding molecular orbitals divided by 2. So we already saw what diatomic hydrogen looks like, H2. So I wanted to show you this again. 1 electron from one hydrogen, another electron from another hydrogen, a total of 2 electrons. So we would go 1, 2, because this is the lower energy. Let me also draw an arrow going this way to show that the bonding orbital is lower in energy than the anti-bonding orbital. Another thing I wanted to mention was that anti-bonding orbitals always have this star, which is indicative of the fact that it's an anti-bonding orbital. So in this case, the number of electrons in a bonding molecular orbital is 2, right here. And the number of electrons in the anti-bonding molecular orbital is 0. So as shown here, it would be 2 minus 0 divided by 2, and we get 1. The bond order is 1, meaning that there's 1 bond between the 2 hydrogens. That makes sense. It's a stable molecule. On the other hand, let's try He2 now. So now we have 2 helium atoms. So 1 helium here, another here. And so helium has 2 electrons, so I drew 2 electrons on this side, 2 electrons on the other side, with a total of 4 electrons in the diatomic molecule. So starting from the lower energy, we would go 1, 2, 3, 4, and we have 2 in the bonding, 2 in the anti-bonding, and once you do the calculation, you would end up with a value of 0. So a bond order of 0 means that this is an unknown molecule. This is not possible because there has to be a bond between the 2 helium atoms in order for it to be a molecule. So this is why He2 actually does not exist, nor does H2 plus, because let's draw out what that would look like. So we always draw out this structure first, and then we have hydrogen on each side, so we have 1 electron, 1 electron. But since it's plus, that means you lost an electron, so goodbye 1 electron. So we're just going to have 1 electron in the bonding 1s orbital. So that would mean it would be 1 minus 0 divided by 2 is 1/2. Again, a bond order of 1/2 doesn't make any sense because you can't just have a half a bond between 2 hydrogens. So again, H2 plus does not exist. It's not a stable molecule. Neither was He2, but H2 is stable. So basically, by being able to draw these MO diagrams, you can figure out the bond order really easily. And it also tells you the likelihood of how stable a molecule is and whether that bond is going to form.
Oh, no,